Hello everyone and welcome back to the Calculus video lecture series. Today in this video we are going to be using what is called a Riemann sum to approximate the areas under curves. So to get us started on this concept and kind of why we do this, let's start with a slightly realistic example. So let's say that a car is traveling at a steady rate of 75 miles per hour from 7 a.m. to 9 a.m. We're going to figure out what is the total distance traveled by the car. And this is a steady rate, meaning that he's going exactly 75 miles per hour for these 2 hours. So if you do 75 miles per hour times the 2 hours that are traveled, you are going to get a total distance traveled of 150 miles. So what we're going to do next is we're actually going to graph that velocity function for the car. Since this is a steady or constant 75 miles per hour, the graph is actually the constant 75. So this is the constant 75. And we are going to section off the interval between 7 a.m. and 9 a.m. So let's just say that this is our sections from 7 a.m. to 9 a.m. Now, this is hard to draw with a stylus, but these are supposed to be straight lines, and this actually forms a rectangle. So this area between the velocity graph, the x-axis, and our 7 a.m. to 9 a.m. forms a rectangle. And we can actually find the area of this rectangle. So the width of this rectangle is the length of our time interval, which is 2. And the height of this rectangle is that 75. So if you found the area of that shaded rectangle, it would be 75 times 2, which is 150. And it is no accident that the area of that rectangle, the area underneath the velocity function, is the total distance traveled. So that's going to hold for really any velocity function. The area underneath a velocity function on a specific time interval is going to be the total distance traveled. So in this case, because the velocity function was a constant function, the area was really easy to find, and velocity is not the only thing you can do this with. This concept can be applied to any accumulated amounts of change. The area underneath the graph of a function will indicate the accumulated amount of change. In the case of velocity, it was the accumulated amount of distance, but if your graph stood for something else, it would just be whatever the accumulated amount of change was. So the last example is really easy to do because the car was traveling at a constant velocity. However, that's not going to be the case for most real-life situations. If the velocity varies at all, the velocity curve is no longer going to form a rectangle. It could form something like this. So the same concept would still apply. You would still section off the area between 7 a.m. and 9 a.m. But however, for a case like this, the area underneath the curve is no longer a perfect rectangle, so it's not going to be as easy to find. So the strategy for cases like this at the moment is we will take that area underneath the curve and we're going to break it apart into a series of rectangles, sort of something like this. And what we will do is we will find the area of each of these rectangles, and we will add them together to get an approximation of the area underneath the curve. Now, this is an approximation. It is not going to be exact. That is why we're using Riemann sums to approximate an area underneath a curve. However, the more rectangles you make, the more approximate the more accurate the approximation. So the more rectangles, the closer the approximation is going to be to the actual area. Also, exactly where and how the rectangles touch the graph also is going to make a difference. Are we going to let the top left-hand corner of the rectangle touch the graph? How about the top right-hand corner? What about the middle of the rectangle? So how the rectangles touch the graph also will affect not only the accuracy, but will also affect your approximation. Now, the rectangles can technically be of any width, and in some instances, there may be cases for having them of different widths. However, for most of the time, and what we are going to do pretty much consistently in this class is what is called a regular partition. So we're going to be dealing almost primarily with regular partitions. A regular partition means that all of the rectangles are of equal width. So they are all the same width, and it's just their height that varies with the height of the graph. So a Riemann sum, that is what these approximations are defined as. It is named after the mathematician who kind of coined this notation. So let's say that a function f is defined on a closed interval a to b, which is divided into n subintervals. So basically, your interval from a to b is broken up into a whole bunch of pieces, and each of these pieces of your larger interval are called subintervals. And there are n of them, and each subinterval is of the same length, width delta x. So each of these subintervals is all the same width, which we are calling delta x. Now, if k is any point in the k subinterval, that means we have three different Riemann sums. So the approximate area under the curve is going to be given by this formula. So you will take the width of the subinterval delta x, that will form the width of your rectangle, and you will multiply it by f of x1, which is the height of the first rectangle. Then you will add to it the area of the second rectangle. So you'll take the width of the rectangle, delta x, and you'll multiply it by the height of the rectangle, f of x2. And then you will keep this going all the way out to the nth subinterval. So you'll take the nth rectangle, take its width, delta x, and multiply it by its height, the height of the nth rectangle. Now, how you let the rectangles touch the graph will give you three different Riemann sums. So if you let the top left corner of the rectangle touch the graph, you have what is called a left Riemann sum. So for a left Riemann sum, that means the x-coordinates that give you each of these heights, the f of x1, f of x2, xk is going to be the left endpoint of your subinterval. For a right Riemann sum, that means that the x-coordinate that gives you the height of the rectangle is going to be the right endpoint of the subinterval. And then another type of Riemann sum that we have is called a midpoint Riemann sum. So this means that you are letting the middle of each rectangle touch the graph, and that the x-coordinate that gives you the height of the rectangle will be the midpoint of the subinterval. Now for the width of each subinterval, because it's a regular partition, all of the rectangles are going to be the same width. That means each subinterval is going to be the same width, which we are calling delta x. So in a regular partition on a closed interval a to b, so a is the left endpoint of your interval and b is the right endpoint of your interval, there are n subintervals, or n number of rectangles. That means the width of each subinterval delta x is given by this formula. So to find the width of each subinterval, you take the width of the overall interval, b minus a, then you divide it by n, the number of rectangles. I think this process is best explained by actually doing one, and we're going to pick a really easy function. We are going to pick f of x equals 1 over x, and we're going to estimate the area under the curve of f of x equals 1 over x with 6 subintervals between x equals 1 and x equals 3. So our interval, our closed interval, is from 1 to 3. That means 1 is playing the role of a, and 3 is playing the role of b. And we're going to let the top left corner of the rectangle touch the graph, so this is a left Riemann sum. So first, before we even draw anything, we do need to find the width of each subinterval, delta x. So the width of each subinterval will be the length of the interval, b3 minus a1, divided by 6. So you get a delta x of 1/3. Which means that each subinterval is going to be of width 1/3. Each rectangle is going to be of width 1/3. And this is between 1 and 3. So we all know what the graph of 1 over x looks like. It looks something like this. However, between 1 and 3, we're really only focused on the first quadrant. So I'm just going to draw a quick first quadrant graph as best that I can. And I'm going to draw it fairly large. And it'll look something like this. And then we have the interval from 1 to 3. And we are going to break up that interval from 1 to 3 into 6 pieces. Now for each rectangle, in order for this to be a good approximation, there can be no gaps between the rectangles, and there can be no overlaps between the rectangles. So that means that the right edge of one rectangle needs to overlap with the left edge of the next rectangle. So each rectangle is actually going to share a side. So the first so we're going to break this apart into 6 pieces, each piece of width 1/3. So if you do 1 or 3/3 plus 1/3, you get 4/3. Then plus another 1/3 and you get 5/3. Then 5/3 plus 1/3 is going to give you 2. Then 2 plus 1/3 will give you 7/3. Then 2 plus 1/3 will give you 8/3. And then 8/3 plus 1 will give you 3. So we're going to let the top left corner of each rectangle touch the graph. So I'm going to take the subinterval from 1 to 4/3 and I'm going to make a rectangle out of it. And I'm going to let the top left corner of the rectangle touch the graph. So it'll look something, oh this is difficult. Oh, this is extremely difficult. I am so sorry. It'll look something like that. Oh, this is not going to be pretty. I'm sorry. All right, so there's your first rectangle. So the height of this rectangle will actually be that point right there, which is the y-coordinate that goes with 1. So that height of that rectangle will be f of 1. Then we're going to take the subinterval from 4 to 5/3 and we're going to make a rectangle out of it. Now these two rectangles need to share a side. So this next rectangle, that was better, goes something like this. So the height of that second rectangle is going to be this point right here, which is the y-coordinate that goes with 4/3, or f of 4/3. Then the next rectangle is going to be between 5/3 and 2, and pretend these are all of equal width. I'm doing my best here. So the next rectangle is going to look something like this. It's going to be formed between 5/3 and 2. So the height of this third rectangle will be this point right there, which is f of 5/3. Then the next rectangle will be between 2 and 7/3, so it'll look something like that. And then the height of this rectangle is going to be this point right here, which is f of 2. Then for the fifth rectangle, our fifth rectangle is going to be formed between 7/3 and 8/3, and it'll look something like that. The height of this fifth rectangle will be that point right there, which is f of 7/3. And then the next and last rectangle will be formed between 8/3 and 3. So that point right there will form the height of your rectangle, and that is f of 8/3. So what we're going to do is we are going to find the area of each rectangle, and then we are going to add them all together. So we're going to take the first rectangle. Now the width of the first rectangle is 1/3. And we're going to multiply it by the height. So the height of that first rectangle is going to be f of 1. Then we're going to add to it the area of the second rectangle. So for the area of the second rectangle, we've got the width of the rectangle, which is 1/3, times the height of the rectangle. The height of the second rectangle is f of 4/3. Then we're going to add to it the area of the third rectangle. So the width of the third rectangle is 1/3, times the height of the third rectangle. Height of the third rectangle is f of 5/3. Then we're going to add to it the area of the fourth rectangle. So the width of the fourth rectangle is 1/3, times the height of the fourth rectangle, which is f of 2. Then we're going to add to it the area of the fifth rectangle. So the width of the fifth rectangle is 1/3, times the height of the fifth rectangle, which is 7/3, so f of 7/3. And then we're going to add to it the area of the sixth rectangle, which is its width, 1/3, times the height of the sixth rectangle, 8/3. Now, if you notice, every single one of these terms has a common factor of 1/3. That is because the width of each rectangle was the same. So just to make this easier, you can factor out a 1/3, and anytime you have a regular partition, you can always factor out delta x like this, and then just multiply it by parentheses, all of the heights added together, as long as you use parentheses. So we're going to evaluate our function 1 over x at each of these points, and I did pick a really easy function on purpose so that finding these y-coordinates would not be difficult. So I'm going to take 1 and I'm going to plug it in for x in my f of x, so 1 over 1 will give us 1 for f of 1. Then for f of 4/3, I'm going to plug 4/3 in for x, that will give us 3/4. Plus that is a 5/3, so we plug in 5/3 in for x and then we get 3/5. Then we're going to add to it, plug 2 in for x, and you get 1/2. Then for f of 3, we're going to plug, for f of 7/3, we're going to plug 7/3 in for x, and that will give us 3/7. And then for f of 8/3, we're going to plug 8/3 in for x, and we will get 3/8. Keep in mind, the only reason that we took reciprocals is because I used the reciprocal function. If you were using, let's say, x squared, then you would be squaring each of these. If you were using x cubed, you would be cubing each of these. So you're just going to evaluate your function at each of these points. And then you can go ahead and use a calculator from here. You should get a sum of approximately 1.218, somewhere around there. So that means that the left Riemann sum approximation for the area underneath this curve is 1.218. All right, so for this next one, we're going to take the same function, the same interval, same number of subintervals, but this time we're going to let the top right-hand corner of the rectangle touch the graph. So this is what is called a right Riemann sum. So this is going to, start the same way. Your delta x is going to be the exact same as it was before, since I'm using the same number of rectangles, the same interval, etc. So your delta x is still 1/3. But this time I'm going to, kind of redraw my quadrant 1 graph, and this time I'm going to let the top right corner of each rectangle touch the graph. So between 1 and 3, your partition is still the exact same, so it's still going to be 1, and then 4/3, and then 5/3, 2, 7/3, 8/3, and 3. So the first rectangle is still formed between 1 and 4/3. However, this time the height of the rectangle is going to be determined by the top right corner. So in a right Riemann sum, your first rectangle will look something like this, and the height of that rectangle is actually going to be that point right there, which is the y-coordinate that goes with 4/3. So the height of the first rectangle is going to be f of 4/3. Then the next rectangle is going to be formed between 4 and 5/3. So since we're letting the top right-hand corner of the rectangle touch the graph, that means the height of this rectangle is that point right there, which is f of 5/3. Then the next rectangle will be between 5 and 2. So the height of that third rectangle is going to be that point right there, which is f of 2. Then the next rectangle will be formed between 2 and 7/3. So the height of that fourth rectangle will be f of 7/3. The next rectangle will be formed between 7/3 and 8/3. So the height of that fifth rectangle will be f of 8/3. And the height of the sixth rectangle will be f of 3. So before I start evaluating the sum, I want to point out something. For a right Riemann sum, notice that we actually used the right endpoint of the interval 3. That was going to determine one of our heights. For the left Riemann sum, notice how we used the left endpoint of the interval as one of our heights. So when we put this all together, because the width of each rectangle is all going to be the same 1/3, I'm going to go ahead and factor out 1/3. And then I'm just going to, use parentheses, and I'm just going to add all the heights together. So the height of the first rectangle is f of 4/3. Then we're going to add to it the height of the second rectangle, f of 5/3. Plus height of the third rectangle, f of 2. Plus the height of the fourth rectangle, f of 7/3. These brackets were a mistake here. Plus the height of the fifth rectangle, which is f of 8/3. Plus the height of the sixth rectangle, which is f of 3. So then what you're going to do is you're going to find the y-coordinates that go with each of these x-coordinates. So if you plug 4/3 in for that x, you're going to get 3/4. F of 5/3 is going to be 3/5. F of 2 is going to be 1/2. f of 7/3 will be 3/7, f of 8/3 will be 3/8, and then f of 3 will be 1/3. Then if you just evaluate this all in a calculator, don't forget to use parentheses, you should get a right Riemann sum of 0.996. So that means that the right Riemann sum gave us an approximation of 0.996 for the area underneath this curve between 1 and 3. Now notice, just changing the type of sum did change the approximation of our area, and this one had a little bit of an over approximation, this one had a little bit of an under approximation. That's not always going to happen. It really depends on your actual function. So if you were to use x squared, for example, that wouldn't exactly be the case. What we're going to do here is we're going to take the same function, the same number of subintervals, and the same interval between 1 and 3. This time, instead of letting one of the corners of the rectangle touch the graph, we're going to let the middle of the rectangle touch the graph. This is what is called a midpoint Riemann sum. Means that we're going to let the midpoint of each subinterval touch the graph. So the width of each subinterval is still 1/3 because I used the same number of subintervals in the same interval. But this time, instead of letting either the right or the left endpoint touch the graph, I'm going to let the midpoint of each subinterval touch the graph. So let's break this up. We still got the between 1 and 3. And I'm going to leave myself a little more space. We've got 4/3, and we got 5/3. Then we've got 2, and we got 7/3, and we got 8/3, and we got 3. Now, the first rectangle is still going to be formed between 1 and 4/3. However, the middle of this subinterval will be what touches the graph. So to find this midpoint, all you have to do is average these together. So 1 plus 4/3 divided by 2 is 7/6. So then the first rectangle is going to be, yes, formed between 1 and 4/3, but the height of that first rectangle will be that point right there. And then the rest of the rectangle will go something, oh God, like this. There we go. And the height of that first rectangle will be f of 7/6. So then for the next rectangle, we're going to do the same thing. We're going to average together 4/3 and 5/3 to get this midpoint right here. So 4/3 plus 5/3 divided by 2 will give you 3/2. There we go. So then the f of 3/2 will be the height of this rectangle, and the rest of the rectangle will go something like this. So that height right there is going to be f of 3/2. Then for the next rectangle, oh, for goodness sake, hold on. Let me fix this. Okay, so for the next rectangle, we're going to average together 5/3 and 2. So 5/3 plus 2 divided by 2 is 11/6. And then we're going to, the height of this next rectangle will be right there, and the rectangle will look something like this. So the height of that third rectangle will be f of 11/6. Then for the next rectangle, we're going to average together 2 and 7/3. So 2 plus 7/3 divided by 2 is 13/6. And then the rectangle will look something like this. So letting the middle of the rectangle touch the graph, the height of that fourth rectangle is going to be f of 13/6. Then for the next rectangle, we're going to average together 7/3 and 8/3. So 7/3 plus 8/3 divided by 2 is 2.5 or 5/2. And then the rectangle will look something like that. And the height of that fifth rectangle will be this point right here, which is f of 5/2. Then for the last rectangle, which is going to be formed between 8/3 and 3, 8/3 plus 3 divided by 2 is 17/6. So the height of that rectangle is going to be f of 17/6. So then to actually find this Riemann sum, you're going to factor out the width of each subinterval, which is 1/3. So the width of each rectangle is still 1/3. We only found the midpoint so that we could get the heights of each of these rectangles, but the width of each rectangle is still 1/3. Then we're going to just add all these heights together. So the height of the first rectangle is f of 7/6, plus height of the second rectangle is f of 3/2, plus the height of the third rectangle is f of 11/6, plus the height of the fourth rectangle, which is f of 13/6, there we go, plus height of the fifth rectangle, which is f of 5/2, and then the height of the sixth rectangle, which is f of 17/6. So then we're just going to take each of these x coordinates and we are going to plug them in for our x, in for f of x to get their actual heights. So if you evaluate f of 7/6, you get 6/7. Plug 3/2 in for x and you get 2/3. Plus f of 11/6 is 6/11. Plus f of 13/6 is 6/13. Plus f of 5/2 is 2/5. Plus f of 17/6 is 6/17. So if you actually do this evaluation, if you actually plug this into a calculator, you get 1.095. So no, before you ask, the midpoint Riemann sum is not simply the average of the left and the right sums. It is a completely separate sum and a completely separate number, so you get 1.095 for your midpoint Riemann sum approximation for the area underneath this curve. Now, as you notice, even with 6 rectangles, writing them all out, all added together, does get to be a lot. I mean, 6 is a manageable number, but really any more than that, if you get, if you have 10 or 12 or, 50 rectangles, writing them all out like that is going to be, really cumbersome, and it's going to be a lot. So we have what is called sigma notation, which is a condensed way of writing large sums. So sigma notation is just a condensed way of writing the sum of a lot of things added together. So for example, the sum of all of the integers between 1 and 99 can be represented in this sigma notation here. So we have a bunch of different parts. Now this k that is inside here, right there, that is what is called the index, and that indicates what is to be summed. So in this case, it's just the integers. If you were adding, the squares of the integers, like 1 squared plus 2 squared plus 3 squared, etc., your index would be k squared. So the index is just what are you adding together. Now this k equals 1 down here, this is what is called the lower limit. This tells you where to start. So in this case we are starting at 1, but sometimes you can start at 0, you can start at 2, but the lower limit tells you where to start. So this tells you start by plugging 1 in for k. Now this 99 up here is what is called the upper limit, and that tells you when to stop. And then this sigma, this is the Greek letter sigma, means add them all together. So what this says is, okay, plug 1 in for k, and then 2 in for k, and keep adding together all of the integers until you get to 99. Now here are a couple of other examples of sigma notation. So for example, if you have the sum of the integers between 1 and 6, that is going to be the sum from k equals 1 to 6 of the integers k. Now if you have the sum of k plus 1 from k equals 0 to k equals 5, it'll look something like this expanded. Here's what the sum of the squares of the integers looks like. Now k is not the only variable that's used for indexes. It can be n, it can be j, it can be anything. So in this case, we are taking the squares of the integers starting from 3 to 7, and we are adding them all together. So we start with 3 squared, and then we add to it 4 squared, 5 squared, 6 squared, and then we end with 7 squared. So you get the idea. Sigma notation is a condensed way of writing repeat sums. Thank you, subtitles. So again, here are just a couple of more examples of Riemann sums. So the sum of the integers, you get the idea. So the left, right, and midpoint Riemann sums can all be written in this sigma notation, and it's really handy to write them in sigma notation if you have a large amount of them. Now, this process of writing the... Oh, good Lord, hold on. All right, so I will say that the process of writing the left, right, and midpoint Riemann sums in sigma notation can be really cumbersome. And for small numbers of rectangles like 4 or 6, it's really not worth it to write them in sigma notation because it's going to take just as long to write them in sigma notation as it will to, just write them all out. But for large numbers of rectangles, we're talking 20 rectangles, 50 rectangles, you're going to want to write them in sigma notation. Now, there is a way to evaluate these sums on a graphing calculator. Once I get the software installed, I'm going to be uploading a separate video tutorial on how to do this on a TI-84, but that is going to come at a later date because I don't have the software yet. But as soon as I do, I will upload that. But what you can do is each Riemann sum is going to be kind of summarized like this. So it will be the sum of all of the rectangles k from the first rectangle to the nth rectangle of the height of each rectangle, f of k, times the width of each rectangle, delta x. Now f of x sub k here is going to be different depending on if you have a left, right, or midpoint Riemann sum. Because as you notice, the height of each rectangle differs depending on if you have a left, right, or midpoint Riemann sum. But the overall sum is going to be about the same. You're going to start with the first rectangle. You're going to end with the nth rectangle. Your interval is still a to b. There are still n number of subintervals of equal length delta x. So if you have a left Riemann sum, that means xk here, what gets plugged in for f of x, is going to be a plus k minus 1 times delta x. If you have a right Riemann sum, then xk, what gets plugged in for f of x, is going to be a plus k delta x. And then if you have a midpoint Riemann sum, that means xk is going to be a plus k minus a half times delta x. So what we're going to do is we're going to use that to evaluate the left, right, and midpoint Riemann sums of f of x equals x cubed plus 1 between x equals 0 and x equals 2 with 50 subintervals. We're going to write the sums in sigma notation, and we are going to use a calculator to evaluate them. Again, I will give you the steps on this slide, and then I will actually show you a full tutorial once I get the software. So let's first start by finding the width of each subinterval. These are all of equal lengths, of equal widths. So we're going to take delta x equals b, which is 2, minus a, which is 0, all over n, which is 50. And that will give us a delta x of 0.04. So let's start with the left Riemann sum. Now, before you do anything on a calculator, I will say that there is a calculator steps to evaluate these, and it does involve sigma notation. Because the TI-84 steps involve sigma notation, you do have to express each sum in sigma notation first before you go evaluating anything. So let's start with the left Riemann sum. Now, xk, which is what gets plugged in for f of x, is going to be a plus k minus 1 times delta x. So in this case, a is 0 plus parentheses k minus 1 times delta x, which is 0.04. So for your left Riemann sum, your xk is going to be, if you distribute the 0.04, you get 0.04k minus 0.04. Then what we're going to do is we're going to plug that xk with parentheses around it into this Riemann sum. So the sum is going to be from k equals 1 to n of f of xk times delta x. So we're going to start from the first rectangle, k equals 1. We're going to go up to the 50th rectangle, k equals 50. Now our f of x here was x cubed plus 1. So when we evaluate f of xk, we're going to plug xk in for that cube right there. So we've got f of 0.04k minus 0.04. and then we're going to multiply it by our delta x, which was that 0.04. So when you actually, simplify this, we're going to get the sum from k equals 1 to 50 of plug 0.04k minus 0.04 with parentheses around it in for that x cubed right there. So we've got parentheses 0.04k minus 0.04 cubed plus 1. So that is f of xk. Then we're going to take all of that with another set of parentheses around it, and we're going to multiply it by 0.04. So when you evaluate this on a calculator, the calculator steps are going to go something like this. For most TI-84s and newer TI-84s, you're going to press the math button, and then you are going to select option 0, which is summation. So math option 0, summation, will give you a sigma notation, and then you're just going to type exactly what you see here into your calculator. You do need a double set of parentheses here, so you do need to type this in exactly like you see it with the parentheses, but when you evaluate this on a calculator, you should get a left Riemann sum of 5.8416. Again, I'm going to do a tutorial later on how to do this on a calculator. You'll just have to hold on for a separate video for that. Then for your right Riemann sum, we're going to do that again. This time, xk is going to be a plus k delta x. So your xk, which will determine the height of each rectangle, is going to be a, which is 0, plus k delta x, which is 0.04k, and that will give us a xk of 0.04k. So we're going to plug this into xk in for our Riemann sum. So we have the sum from k equals 1 to 50 of f of xk, which is 0.04k, times delta x, 0.04. So then our function is x cubed plus 1, so we're going to plug 0.04k in for x in our f of x. So that will give us the sum from k equals 1 to 50 of plug 0.04k in for x, so 0.04k, parentheses cubed, plus 1. Then you're going to take all of that with parentheses around it, and you're going to multiply all of it by 0.04. And again, if you do math option 0, summation, and then type this in exactly like you see it written here, you should get a right Riemann sum of 6.1616. So I have to do the midpoint Riemann sum on another slide because I ran out of room. So for the midpoint Riemann sum, our xk, which will determine the height of each rectangle, is going to be a plus k minus a half delta x. So our a is 0 plus parentheses k minus 1/2 times delta x, which is 0.04. And I'm going to simplify this by distributing the 0.04, so that will give us 0.04k minus 0.02. Then I'm going to take this with parentheses around it, and I'm going to plug it into my sum. So I have the sum from k equals 1 to 50 of f of xk, which is 0.04k minus 0.02 times delta x, so times 0.04. Then remember your f of x is x cubed plus 1, so you're going to take 0.04k minus 0.02, and you're going to plug it right in for that x there. So we will get the sum from k equals 1 to 50 of, plug this in for x, so we have 0.04k minus 0.02, parentheses cubed, plus 1. Then you will take all of that with parentheses around it, and you will multiply it by delta x, so multiply it by 0.04. And then if you press math, option 0, which is summation, and type this in exactly like you see it here, you should get a midpoint Riemann sum of 5.9992. So as you notice, this process is really cumbersome. So the process to even use a TI-83 or TI-84 to evaluate this is really cumbersome. So you're really only going to want to do this when you have a really large, kind of unmanageable number of rectangles. For small and manageable numbers of rectangles, like 4 rectangles or 6 rectangles, this process probably isn't worth it. And I wouldn't recommend this process. You're probably better off just drawing a graph, figuring out the area of each rectangle individually and adding them together. So really only use this process if you have a large number of rectangles. Now I will say that this math option 0 is really for newer TI-84s. So for newer TI-84s, it is going to be math option 0. For TI-83s, you're going to have a different set of steps. So for TI-83s, you're going to press the second key. You're going to press the stat option, go over to the math option, and select option number 5. This is sum. Then immediately after that, you will press the second key again, go back to the stat menu, so second stat again, go over to ops, and then select option number 5. For 83s, you will get something like this on your home screen. You will see sum of sequence. And then what you're going to do is you will type in your function, whatever you're evaluating. In this case, you will type this in right here, comma, your variable, x, comma, first rectangle 1 to the 50th rectangle 50. So, you would plug, all of that in for right there. So for TI-83s, this is unfortunately what you're going to have to do because the TI-83 does not have math option 0. If you have a TI-83 and you have any questions on this, please email me and let me know because I will be happy to answer it. But for most of you who have a TI-84, math option 0, and just type in your sum exactly how you see it here, it's pretty straightforward. Now, I will say that for all of these sums that we have given so far, we were all dealing with areas above the x-axis, so they were all positive. However, I will say that if you have an area that lies below the x-axis, that is going to actually be a negative value. Because remember, these areas represent accumulated amounts of change. So, for example, in the case of velocity, remember you can move backwards. So any movements backwards would give a negative velocity, which the velocity function would go below the x-axis to indicate a negative displacement. So if you have an area that lies below the x-axis, it's going to have a negative value. Now, if you have, let's say, a sum of some areas that are above the x-axis and some areas that are below, a straight Riemann sum would just give you the net area of that region. So the net area of a region R is formed by taking the sum of all of the areas above the x-axis and then subtracting all of the areas below the x-axis. So for example, for this diagram right here, we obviously have some areas that are above the x-axis and some that are below. So given this picture, we're going to find the net area of our function f of x from x equals a to x equals c. So it obviously breaks apart at b. So at b, it transitions from being above the x-axis to below the x-axis. So the net area is going to be all of the areas above the x-axis as positive numbers, so that'll be 12, minus the areas below the x-axis, or you can think of it as adding to it the negative area that's below the x-axis. Because remember, subtraction is the same as adding a negative. So you'll take the area above the x-axis, positive 12, you will add to it the area underneath the x-axis, negative 10, and that will give you a net area of 2. So for a net area of 2, that means there is slightly more area above the x-axis, but a lot of the area above the x-axis was canceled out with the areas below. So just be careful that a straight Riemann sum, if you ever dip below the x-axis, will always give you net area, and it will take any areas below the x-axis and count them as negatives. So that is it for Riemann sums and approximating areas under curves. So thank you all very much for watching, and we're actually going to pick up with this concept again in the next video when we cover what is called the definite integral. So thank you all very much for watching, and I will see you in the next video.